Hey folks, so we are now talking about the not pooled or Welch's, also known as the unequal procedures. This unequal variances, not pooled or Welch's two-sample hypothesis test or confidence interval is what we use when we've met all of the conditions for the pooled t-test except for either equal sample sizes or nearly equal sample sizes or equal standard deviations. So when we can't meet one of those two conditions, it kicks us into this test. So we're going to want our hypotheses, our conditions, our sampling distribution. We write our hypotheses the same way we wrote the hypotheses in the last section. So I'm going to move pretty quickly through some of the details here. You guys may need to pause the video to read. So our hypotheses are still mu1 equals mu2 versus they're not equal, they're greater than, or they're less than, or we can write them as the subtraction statement. The conditions for this unequal variances or not pooled test or confidence interval for the difference of means is still that we have a random sample or two random samples, normality with the same normality conditions, and then we have not paired data. The difference now is that population standard deviations are considered unequal or we didn't have equal sample sizes. So the conditions we have to meet are random sampling, normality, and remember the conditions for normality. We can have each sample as normal because we're told so. The graphs of each sample are rounded and symmetric, or the graphs of each sample are similar in shape without any big outliers, or we can use that large sample central limit theorem where n1 plus n2 is greater than or equal to 40. We have independent data or not paired. And then population standard deviations are considered unequal. We don't actually say this. This is what we tried to show with the pooled test. So either N1 is not approximately equal to N2 or S1 over S2 is not less than 2, or S2 over S1 is not less than 2. So any one of these three things is not true, and it kicks us into the not pooled test. We don't actually show this, so we don't say or show this step. All right. So our test statistic, if the conditions on the previous slide are met, the test statistic for the not pooled or the unequal variances t-test is approximately a t-test statistic, and it's very similar to the last one. It's x bar 1 minus x bar 2 minus mu1 minus mu2, where mu1 minus mu2 is almost always 0. Over, and because we have said that these standard deviations or sample sizes are not equal, we use the square root of S1 squared over N1 plus S2 squared over N2 as our standard error for these two sets of data together. The degrees of freedom is actually this weird formula that you see here. This degrees of freedom, remember, we need for the t-distribution because the higher the degrees of freedom gets, the closer this t-distribution gets to the normal. It changes with every single degree of freedom. And this particular set of degrees of freedom formula is called the Welch-Satterthwaite degrees of freedom formula. There are other formulas out there, but this is the most commonly used one. And this is one of the reasons why stat packages are so nice, because you can imagine we can all do this math, but it would be an error waiting to happen. So we'll use R to calculate that for us. So the unequal variances, the not pooled two-sample t or the Welch's two-sample t confidence interval looks a lot like the previous confidence interval. It's x bar 1 minus x bar 2 plus or minus some t statistic times the standard error, but the standard error here is the square root of S1 squared over N1 plus S2 squared over N2. So again, we have our statistic plus or minus our margin of error in both sides. And then this thing here, the bottom part gives us our lower bound, the upper part gives us our upper bound, and we are trying to estimate mu1 minus mu2. So this is almost exactly the same as the pooled case. The formula just changes a little bit. The conditions here for this confidence interval are the same conditions that they were, same conditions as not pooled t-test. So the conditions we just went over on the previous page are the same for both the hypothesis test and confidence interval. The two-sample t statistic is most robust when both sample sizes are equal and both sample distributions are similar. But even when we deviate from this, the two-sample tests tend to remain quite robust. As a guideline, a combined sample of N1 plus N2 of 40 or more allow you to work with even the most skewed distributions because the central limit theorem is working. Statisticians do not agree on when to use the pooled versus not pooled procedures. I've given you guys some rules to follow, but not all people will follow these rules. Some fields only use pooled, some fields only use not pooled. And if you conduct the pooled versus the not pooled test, you'll see that the p-values are very similar to one another. There are situations when Welch's procedures are more powerful, and there are situations when the pooled procedures are more powerful. We have a set of rules that we are going to follow in this class. So let's do our first example. The central tail feathers of the long-tailed finch are a sexually dimorphic trait hypothesized to play a role in sexual selection. It's believed that longer tail feathers in males cost energy to produce, and this is thought to signal the male's excellent health condition. Here are the lengths of the tail feathers, average of the two central tail feathers in millimeters, of male and female long-tailed finches. Test to determine if the average length of male tail feathers is really longer than females, and the data are in the Finch Excel file. Before we start our hypothesis test or our confidence interval, we're going to take a look at our statistics and the side-by-side box plots, as well as those graphs for normality. So I'm going to go ahead and start writing some of this down. Our hypothesis, P-O-T-H-E-S, the hypotheses. The null hypothesis is that the mean for male tail feathers is equal to the mean of female tail feathers, and the alternative is that the mu for males is longer or bigger than the mean for females. If we write these as subtraction statements, order matters. So be careful, mu male, we subtract mu female on each side, we get mu male minus mu female is greater than 0. We do want to calculate X bar for males, sample size for males, and sample standard deviation for males. We want X bar for females, N for females, and sample standard deviations for females. We're going to pull the histograms or the QQ plots for both for males and females, and we're going to do the stat box plots. And then you would pull these into your notes, which I can't do here in OneNote. The conditions that we're going to try to satisfy are random sampling, normality, and we want to look and see if N1 is approximately equal to N2. Oh, and not paired, by the way, not paired or independent. And then we use N1 is approximately equal to N2, and sigma 1 is equal to sigma 2. If we cannot satisfy either one of those two, it kicks us into not pooled. So let's start working on this in R. I've already pulled my finch data in, and I want to show you this finch data because this is something new to you guys. So my males, I have a bunch of male tail feather averages. There were 27 of those. And for the females, we only have 14. And so notice that when I bring my data in like this, I get a whole bunch of NAs. And I'm going to have to deal with that because I'm not going to be able to calculate some things. So this is the two sample T procedures, and I'm going to do my box plot first. My box plot we do just the same way we did in the last module, so I'm not going to spend any time on it. You guys can look at that code yourself. My box plots are here. The female box plot. So when I look at this box plot, the female box plot is pretty much lower than the male box plot, and certainly the median is significantly lower than it is for the males. So that makes me think that we're going to find that there is a difference when we look at these. I'm also going to calculate my statistics. So the first thing I'm going to do is look at my male statistics. So I'm going to calculate the mean, the standard deviation, and the sample size for my males. So mean is 89.2, sample size is 27, and standard deviation is 11.4. And then we're going to work on the females, and we're going to run into a problem, and that's because of those NAs. That means not applicable, and that's because we didn't have as much data as we did for the males. So I'm doing the exact same thing I just did for the males, but what you're going to see is mean of females NA real is an error. What it's saying is you have numbers here that are not numbers. NA is not a real number, and they wanted it to be a real number. The same thing was female. And I also want you to see that the sample size for females was 27. But if I go back to this finch data, I only have 14. So this is one of the reasons why we always look at our data, and we're going to have to deal with this problem. So the problem that we're dealing with is missing data points in this data, and we need to get R to ignore this by using the NA.remove equals true function. And so we do that by doing mean of females is equal to mean of my data frame $ variable, comma, NA.remove equals true. So that will work for both the mean and the standard deviation. What's happening there is I'm telling R, calculate the mean and the standard deviation, but remove those NAs. So I'm going to go ahead and do that again. I'm going to run it, and those show up on the right. So I get the female mean is 63.2. and the female standard deviation is 7.4, but I did not get sample size yet. When we do sample size, what we actually try to do, if you do this length of the female finches, remove the NAs, I get an error. So I can't count the number of rows without the NAs. R doesn't handle that. So now I'm going to show you what we're going to do. We are literally going to use R to count. Is there a number in this row, or is there not a number in this row? And I'm going to type this in the console down at the bottom because I don't want to save this code. I just want to show you guys what's going on. Is NA, so I'm saying is the NAs of the finches females. F-E-N, females. There we go. So N is NA of the finch females. So what that gives me is all of the rows that had numbers, it tells me they're false. All of the rows that had NAs, it tells me there are trues. But if I want it to count only the ones that had falses, I need to tell it to count the nots. And the function for not is an exclamation point. Exclamation point is .NA of Finch, $ females. And notice I'm doing the exact same code I did above, but I'm using the not function, which is that exclamation point, run. And so what happens is it's now saying, true, there's a number in row 1. True, there's a number in row 2. And it goes on and on until we get to row 15 or whatever it is. And then it says false. So what I want to do is count the trues. And that's what I have done up here with this code. N of female equals length of the finch females where exclamation point is .NA of finch females. So we're saying count the finch female rows that are true, but we had to do not NA to get that. So this code, by the way, I just copy my code after I get it once. I just go back to a previous file and look at it so I don't have to think through this. When I run this code, it counts my females as 14. Of course, the other thing we could have done here is we could have just looked at this data. If you don't have a particularly large data set, you do not have to do that particular line of code. You can just look at it and see that it's 14, and that would be your answer. I'm going to quick look at the histogram for each of these. The histogram of the males, that's relatively normal. We have a peak in the middle and no major outliers. The histogram for the females is a little bit skewed to the right. So I'm going to take a quick look at the QQ plot for each of these. QQ plot for males is, it's not great, but it's not bad. And then the QQ plot for the females, again, it's not bad. So both of these would get me normal enough. But remember, we only have to have 40 pieces of data between the two groups. Well, 27 plus 14 is 41. So central limit theorem will work here as well. So let's go ahead and put some of the stuff in the notes. So I have X bar for the males is 89.2. Sample size for the males is 27. Sample standard deviation for the males is 11.4. Females, sample mean 63.2. That's way lower. Sample size was 14 and sample standard deviation 7.4. We would look at these histograms, see R for this, and then the stacked box plot, we need nice graphs for this one because these are the graphs that we'd actually publish. And just real quick, I'm just going to sketch them, but we would normally pull these in. So I have a box plot that has a line in the bottom end. And then that's for my females. And then for my males, that box plot starts really at the top of the other bar at the third quartile. So I've got a box. And so we can see that the males is much higher than the females. We would certainly bring in actual graphs here using good graphing skills. Use good graphing skills for this box and whisker plot. So our conditions, random sampling, probably not because this is something in the field, but again, this is one that's often ignored. Normality can be met through the central limit theorem because 27 plus 14 is greater than or equal to 40. Not paired, we don't have paired data. We have males and females and they're not of no relation. And then 27 is not even close to 14. And so when that happens, we do not use pooled. So notice when I showed that N1 was not equal to N2, I didn't even look at standard deviations after that. So when that happens, we use the not pooled t-test or the t-interval, either one. So now that we know we didn't meet the conditions for pooled, it kicks us out into not pooled. And so that's what we want to do in R. So I'm going to go back to R. We're using the exact same t-test function. The difference is this time we use variances are equal is false instead of true. because we're saying that they were not equal. So either sample sizes or variances are not equal, either one. Everything else stays the same. So I have t.test of Finch $males because I wrote males first in my hypotheses. Finch $females was second. The mean difference is equal to 0. My paired data, it's not paired, so I say false. Var.equal is false because I'm using not pooled or not equal variances for this one. And then the alternative was a greater than alternative, so I'm going to run that t-test. And my test, notice this is the Welch's two-sample test. Welch's test is the not pooled or unequal variances test. My test statistic T is 8.77, and my p-value is 7.4 e to the negative 11th, or effectively 0. All right, let me write all that down. So I did my not pooled or Welch's t-test. I got a t-test statistic of 8.77. That's way big on the t-score. And then my p-value was effectively 0. And so what we're seeing in this t distribution, 0, 1, 2, 3, 4, 1, 2, 3, 4, we would be way up here somewhere, and our p-value would be effectively 0. So now we can make our decision. And our decision, remember, our p-value is compared to alpha. I don't particularly care what alpha is here because my p-value is 0. So alpha of 0.01, 0.05, and 0.10 doesn't matter what field you're in, we would reject the null. Everybody would reject the null with a p-value this small. And then our conclusion then is there is evidence, and it's strong, there is strong evidence because our p-value is 0 to show, and I'm going to go back and look at my hypotheses, that the mean tail feather for males is bigger than females. To show that the mean tail feather, of males is bigger than the mean for females. All right, that's it for this lesson.